In this video, we'll start with the next experiment, that is the use of flip-flops. The aim of this experiment is to design and implement gate level as well as MSI circuits of flip-flops. Flip-flops are very commonly used in digital circuits in order to store binary data, and this binary data can be changed using different inputs. There are around 4 flip-flops that we'll cover in this experiment. They are the RS flip-flop, the JK flip-flop, the D flip-flop, and the T flip-flop. The apparatus that we require is the baseboard, a couple of ICs, and a few jumper wires. The procedure that we have for this experiment is quite similar to the ones before. You'll have to mount either the logic gate or the desired IC in any one of the 10-pin sockets on the board, and using the provided pinout diagram, you'll have to make connections to VCC, ground, as well as the input and output pins. Connect the VCC to +5 and the ground to the ground pins, and the input can be connected either to +5 or to ground depending on the test case. And you can observe the output by connecting the output pins to the LED box or the 7-segment display. Then after this procedure is done, you can verify the truth table for all the flip-flops. So the first flip-flop that we have is the RS flip-flop. It has two inputs, R and S, and it also requires the clock. So when both R and S are equal to 0, there will be no change in the output. So if initially the value at Q was 0, and if R and S are set to 0, the value of Q will still be the same. So the state will be no change. In case we set S as 1 and R as 0, in that case we can say that the flip-flop has been set and the output that we get at Q will be 1. And in another case, if we set S as 0 and R as 1, then we can say that the flip-flop has been reset and the output that we'll get at Q will be 0. And Q dash over here represents the complement, and it will always be opposite to what Q has. But we have a fourth case over here where S and R both are 1, and it is a forbidden condition because in this case both the outputs, that is Q as well as Q complement, become equal, which is something that should not happen. So in order to overcome this fourth case, we have a modified flip-flop known as the JK flip-flop. The JK flip-flop again has two inputs, J and K, along with the clock pulse. And this is how its implementation looks like with the logic gates, and this is how the IC package looks like. So we have, it is very similar to the RS flip-flop, where in the first case where both of them are 0, we have no change in the input. If J is set to 1, then the flip-flop is in the set state, and if K is set to 1, then the flip-flop becomes reset. But in case both J and K are 1, then the output will be complemented, and it will toggle. So this is still better than what we obtain at the with the RS flip-flop. Then the next flip-flop we have is a very simple flip-flop known as the D flip-flop. It has only a single input called as D, and the output that this flip-flop provides is equal to the input itself. So looking at this truth table, if the D input is 0, the output at Q will also be 0 and Q complement will be 1. Similarly, if the D input is 1, the output will be 1 and the Q complement will be 0. And this is how its implementation looks with the logic gates, and this is how the IC packet looks. The next flip-flop that we have is the T flip-flop. This is very similar to the JK flip-flop, and in this case, both the inputs of J and K are basically shorted together. This is how the implementation looks with the logic gates, and this is how the IC packet looks. So since J and K are shorted, there will be only one case where T can either be 0 or T can either be 1. So if T is 0, then the output of the flip-flop will be equal to the previous state. So if T is 0 and the previous state was also 0, the output we'll get is 0. But if T was 0 and the previous output was 1, then the output should be 1. And if we set T equal to 1, then the output will start toggling between 0 and 1. And in the next part of this video, we'll demonstrate how you can implement the JK as well as the D flip-flop using the mobile lab. In this part, we'll demonstrate how to implement the JK flip-flop through the IC7473, and we'll also verify the truth table.
Now let us start with the implementation part. So here IC7473 is already mounted. So at first we will connect VCC and ground. So pin number 4 is VCC and pin number 11 is ground. After that, pin number 14 is J. Second is clear bar, so it must be connected to plus 5 volt. After that, pin number 3 is K. And pin number 1 is the clock. And pin number 12 is our output. So that was our connection. Now let us verify the truth table. So here both the inputs are connected to the ground, which means both are logic 0. So the output must be previous state. So it is by default logic 1. If you make pin number 3, if you make K as 1, then the output must be 0. So yes, here we can see that the output is 0. If J is 1 and K is 0, let us check that straight. So LED is glowing, so we can say that when J is 1 and K is 0, the output is logic 1. Now let us check for 0 0. When both the input are 0, the output must be previous state. So our previous state was logic 1. So here when both the inputs are 0, here it is still showing logic 1. So we can say that when both the input are logic 0, then the output is previous state. Now what if both the inputs are logic 1? So according to the truth table, the output must be toggle. Let us check. So as both the inputs are given logic 1, we can see that the LED is blinking continuously. So we can say that it is in the toggle state.
In this part, we'll demonstrate how to implement a D flip-flop, that is the IC 7474.
To implement D flip-flop, at first you will have to refer the pin diagram of IC 7474 given in the manual. Now let us start with the connection. So pin number 7 is ground and pin number 14 is plus VCC. So that pin number 1 is clear bar, so it must be connected to the 5 volt. Pin number 2 is 1D, which is our input. Pin number 3 is clock. And pin number 4 is preset bar, so it must be again connected to the plus 5 volt. Pin number 5 is our output, and pin number 6 is output bar, so it is not useful for us right now. So this was the connection, and the output of D flip-flop is nothing but the input. So if we give input as 0, the output must be 0, and if input is 1, then output must be 1. So let us check it now. So here we can see that input is ground, which is logic 0, so the output is 0. Now here when we give input as plus 5 volt, which is logic 1, the LED starts glowing, which means that the output of the flip-flop is 1.